recording. What we're doing today is we're preparing for your next exam, which is coming up this week. So exam 3 will be like the other two, where you do it online. And then there's a separate assignment in which you would upload work. Okay, so what we're doing today is kind of a practice run for the exam. This covers pretty much the applied problems that we've dealt with implicit differentiation as well as with integration. I know I said in my previous email it just covers integration, but it also covers the implied differentiation stuff and the application problems for differentiation. And that's pretty much what I want to focus on today. Okay, so again, my idea here is not to, spend a lot of time doing integrals and integrals and integrals. I want to get through the applied stuff first. So I'm going to begin by sharing my screen with you. And I'm going to start with the browser. And we're going to go into our course, and I'm going to show you where we are in case you want to follow along. We're currently in week 12, and that means there's about 4 weeks left to the semester, 5 if you include this week. Okay, the live online sessions will go here, as well as the work that I show you for solving the practice problems will go here. I'm going to pop this open just because there's an interesting note in here, and I want to make sure everybody sees it. Okay, there is no class on Wednesday. Okay, Wednesday is a Maricopa Community College district holiday in honor of Veterans Day. Okay, there will be no class. So this live online class is the only one we'll have this week. Okay, if you have other classes that meet on Wednesday, you should double check, but your instructor should not be holding a live online class because it's technically a district holiday. Okay, so going back to my modules, and pop back down there. Here's what I wanted to show you. Okay, the practice exam for exam 3 is the file I'm going to be using today. So if you want to print this off and follow along, feel free to do that. Like I said, I will upload my work, so you'll have anything that we do today to review along with the video. Here is, again, please read these carefully. Exam 3 is the actual exam. Please don't open it until you're ready, okay, to take the exam, because, again, you're only going to be allowed to open it once, okay? It is timed. I will open it for you just so you can see directions. Hopefully, those will pop up. Okay, so you have an hour and 40 minutes. Okay, finish it in an hour and 40 minutes. It's due Sunday, November 15th at 11:59 p.m. Please don't open it at 10 o'clock, okay? I mean, that's not really, yes, you can finish it at that time, but it would be better if you gave yourself more of a buffer in case there's any problems, okay? Again, use your calculator, your notes. You can use, and I will change these directions. You can use anything from the course, okay? Any notes, any video, any of the calculators I put in the course, I'm okay with that, all right? Use whatever tools you can find. You want to look stuff up on the internet? Go for it, okay? I would hope, though, you would actually try to solve the problems yourself, okay, rather than collaborating with somebody else or using some sort of a tool to actually do problems. You know, most of them are applied problems, okay? Those, you're not going to be able to Google those, okay? Again, what I would like you guys to do, there's a separate assignment in here besides the exam. Again, it takes a minute to pop down there. There's a separate assignment besides the exam called exam 3 work. No points for it, but upload your work, okay? Do it after you submit the exam. You can take photos of your work, and there's free online apps that put those into a PDF. You can upload the original photos from your phone. If you've got a scanner and you want to scan the work in and upload a PDF, whatever, but send me work. That way I can give you partial credit. I'll go through every single one of the exams and regrade them to try to give you some partial credit. Because I know from my own personal experience as a grad student, taking online exams is awful because the computer either grades it right or wrong. Even if you've gotten 85% of the problem right, it still grades it wrong if you made a mistake at the end. Okay, so that's why. Please upload the work. All right. Also, this grade check will probably not include your exam 3 grades, but do the grade check. See if you can find your grades in Canvas and take a special note of what you've got that's incomplete. Okay, and if you've got any concerns at all when you submit the grade check, communicate with me. Okay, I read every single one of these and I respond to them. Okay, so again, we're about 5 weeks out from the end of the course, and I want to make sure everybody in this class can successfully complete MAT213. So again, this is a communication opportunity, so please take advantage of that. All right, so at this point, anybody got any questions? Okay, questions on the housekeeping? Anybody questions about the exam, about your grades, any of that stuff, other than a specific question of why is my grade such and such? Okay, we're good. All right, so again, pretty much the same scenario as before. That's how we're going to do this exam. All right, and the final will be similar. Okay, the only difference is the final will be cumulative rather than just covering a section of the course. All right, so if you give me a moment, I will connect my tablet and we can start looking at the review questions. Oops. Okay. All right, let me share that with you. All right, so everybody should be seeing a file called Practice Test 3. Okay, now these practice tests have similar questions to the ones on the exam. Are they identical? No. Okay, because the point of the exam is to understand the type of question and to understand how to solve that type of question. Again, it's really more about being able to set up the problem and being able to interpret what came out of your math, okay, than it is to actually be able to crank through the steps, right? It's a beginning calculus class, so yes, I'm going to ask you to show steps. Okay, but again, I'm trying to make it more relevant to what you would do in the real world. So this first problem is asking you for the derivative. Remember, dy dx is like asking for y prime. Okay, it's the same thing. Okay, the only problem is this equation is very difficult to solve for y because, as you can see, I've got y's everywhere, okay, and one of them is raised to the 4th power, so I need to take a 4th root in order to solve for y here. So in other words, what I need to do is to differentiate implicitly. Okay, with respect to x. How do I know it's with respect to x? Because dx is on the bottom of this differential. Okay, so I'm differentiating as if x is my independent variable, which it is. Okay, so what does that mean? It means whenever you see an x, you can differentiate it normally, but whenever you see a y, you're going to treat y as if it's a function of x. So treat y as a function of x, like it's a composition, and you're going to use the chain rule. Okay, if you remember the stuff we did about implicit differentiation, that's pretty easy because if I don't know what the function y looks like, I can't isolate it. Then anytime I differentiate the inside, the y function, I'm just going to get a dy dx. And then the last step is to try to solve for dy dx. Okay? All right, so let me get started with this. And get rid of that. Okay, so basically, if you take a look at this function, you can see I've got x's multiplied by y's here. This first term's a product. Okay, so I'm going to need to use the product rule on it. X is just my independent variable, and y is a function of x. Same thing in this term. It's a product of x's and y's. So this requires the product rule. That requires the product rule. Okay, this term is simply a function. It's just x, so that's easy to differentiate. Here's y, but there's no x's mixed in. So this is like differentiating a composition. Okay, everybody understand it's important to look at it first, okay, so you can see what the pattern is and you understand how to begin differentiating. Okay, don't just jump in and do calculus, okay? So again, I've got two products. So let me first start with the x, y fourth, okay? So I'm going to say let u be the x, let v be y to the fourth. Okay, so I'm doing the product rule off on the side. U prime is simply 1. Remember, I'm differentiating with respect to x, so that's fine. Okay. V prime is going to be 4y to the third. That's the outer function. And then the inner function would be dy dx. So that's the chain rule part. Okay. Is everybody okay with that? And then the chain rule pretty much says, take u, multiply it by v prime, and then take v multiplied by u prime. Okay, so let me do that. So first I have x, that's u, times v prime, plus, okay, v times u prime. Okay, so there's my first product rule. Again, I'm kind of constrained for space here, so I'm not writing out as much as I ordinarily would. Okay, again, when you take your exam 3, please make sure you've got your cheat sheet for derivatives. You've got your cheat sheet for integrals. Just have all that stuff handy so you don't have to go looking for it. Gather all that stuff together before you actually start the exam. Okay? All right. Then I have another product. So here's product 1. Right? I'm going to go up here for product 2 since I don't have room anywhere else. Okay, product 2 is the second one. Okay, x squared and y. So I'm going to say u equals x squared, v equals y. Okay. And then to differentiate, this is just x, so I get 2x. Differentiate it normally. Okay, but when I differentiate y, I differentiate the outer function. Y gives me a 1. Then the inner function is the y that I can't see, so its derivative is dy dx. Okay, then I'm going to use the product rule one more time right here. And I'm going to say u times v prime. I don't need the 1, so I'm just going to put dy dx. That's u times v prime plus v times v prime. Okay, everybody all right with the derivatives of the products? Anybody questions at this point? All right, then I have an equal sign. Remember, I'm just differentiating everything in place, okay? So now I'm going to differentiate the other side of the equation. Okay, I have an x there. That derivative is 1. And then I have 3y. Okay, well, if I differentiate the outside function, 3y, I get a 3. Right? Because again, you drop the exponent on y, it goes from 1 to 0. So I wind up with just the 3. And then the derivative of the inner function is dy dx. Okay? So that's the calculus step. Right? That's the calculus step. The rest of the problem is algebra. Okay, the rest of the problem is algebra. So the next part is isolate dy dx. And that involves getting all of the terms with dy dx in them on one side of the equation and everything without dy dx on the other side. Okay, I've got two terms with dy dx here. I'm going to leave them there. I'm going to subtract this term. Yes, that'll be over here. And then I have to subtract this term to get it over here, and subtract this term and get it over here. Okay, so first I'm going to do a little bit of organizing, okay, to make these things look a little bit more algebraic. Remember, within each term, all of the factors are multiplied. X is multiplying 4, which is multiplying y cubed, which is multiplying dy dx. So that means I can rearrange the terms to look like anything I want. Now, having done algebra for decades, it looks neater to me and it's easier for me to see what I've got if I put numeric coefficients first, multiplied then by x variables, multiplied by y variables, and then dy dx on the end. So my first step is just going to be to reorder these terms to make them look like that. So this first term is going to be 4xy cubed dy dx. Again, you don't have to do this, but again, I find if I don't do it, I tend to lose things. The next term is just y to the fourth. This term doesn't have to change, x squared dy dx. And the last term, I'm going to make 2xy. And again, on the other side, nothing has to change. Okay, what's nice about this equation is everything's positive. So I don't really need to say, show the actual subtractions to do the algebra. Okay, I'm just going to, anything that winds up on the opposite side of the equation will have a negative sign in front of it, right? So when I move y to the fourth and 2xy over here, they'll have negative signs. When I move the 3 dy dx over here, they'll have a negative sign. Okay, so here's my moving things to opposite sides. Okay, and then on this side, I'm going to have 1 minus y to the fourth minus 2. Okay, so there's the algebra part. Okay, the first part of it was just writing things in a more algebraically conventional way. Okay, and then the second part was moving the furniture across the equal sign. Okay, so now I have all the terms with dy dx over here and all the terms without dy dx on the right-hand side. Okay, so the next step is factor out, which means divide out dy dx from all the terms on the left. All right, the very last step is divide by the quantity in parentheses, which gets rid of it on the left and just leaves dy dx. And it divides the quantity on the right-hand side by the quantity in parentheses. Okay? And that was what you were asked to do. You were asked to find dy dx. Okay, everybody all right with 1? Okay, with implicit differentiation? Anybody questions about it? Okay, good. Right. Realize you can also, and I believe there's an applied problem later on in the review, where you can differentiate both x and y if they are functions of time. Remember, those are problems like the ladder sliding down the wall or the spreading oil slick, okay, where you've got two variables that change as functions of time. Then you're differentiating them both implicitly with respect to t, okay? So that is also implicit differentiation. That turns out to be super really handy when you're dealing with real life situations that are changing. Okay. All right. So next problem says find the equation of the tangent line to this curve at the point 1, -1. Okay. Let me ask you, and again, feel free to unmute or put it in the chat. Okay. Give me an idea of what do I do first? What do I do first here? You need the equation to a tangent line. Tangent line's a straight line, right? So what do you do first? Okay, Tu Yen says, find the slope. Okay, find the slope. Great. Now, how do you find the slope? You're absolutely right. Anybody have any ideas? Okay, Tu Yen saying find dy dx, and she's probably using differential notation for it because you can't really solve this equation for y well. Okay, you could, but it'd be messy. Okay, so she's saying let's differentiate this implicitly with respect to x, right? I'll get dy dx. Now you need a slope. A slope is a number. So how are you going to find that number? You're going to plug in these values here for x and y. Okay? So again, it pays to have a roadmap of how to begin these problems. You're going to find the slope. You're going to do that by finding dy dx implicitly and then use the given point to actually evaluate dy dx. Okay? At the point of tangency. You know this point's on the line because it's where the tangent touches the curve. Okay? All right, so first we're going to be by implicitly differentiating this function here. Again, this is a product, so I'm going to start out by differentiating the product. I'm going to say let u be 5x, let v be y. That means u prime equals 5. V prime is 1 times dy dx. Okay, so there's my product rule. Okay, and then again, it's u times v prime plus v times u prime. Okay, and again, the order you do it in doesn't matter. Okay, so I'm going to start with my u times v prime. I don't need the 1 plus v times u prime. Okay, I'll come back and I'll algebraically simplify it in the next pass. Separate the calculus from the algebra. You try to do them both at the same time. Unless you are very, very comfortable with algebra, you tend to make mistakes. Okay? So that's the product rule. Then let's do this. Okay, this next term is purely x's, so I'm just going to differentiate it normally using the power rule. Bring down the 2, multiply the 3, drop the exponent by 1. And now I'm going to differentiate the other side of the equation. Okay? All right, y is a function of x, so the derivative of the outer function's a 1. The derivative of the inner function's dy dx. And then the last term is negative x, and the derivative of that is minus 1. Okay, that's the calculus part. Everybody good with that? Okay, please, if you ever see me make a mistake when we're in class, please call it out. Okay, I really, really would appreciate that. Okay, I try to be as careful as I can, but sometimes when you're handling technology and writing and a whole bunch of other things, you know, you make mistakes. I appreciate it if you call me out on a mistake. Okay, so here, next we're going to isolate dy dx. And that involves the same thing, okay? It involves getting everything on one side of the equation with dy dx's. So these two are going to be over here. So this dy dx will have a negative sign. I'm going to write this as 5y. It's going to wind up over here with a negative sign in front. Okay, so let me do that. So this stays here. Okay, the negative dy dx comes from the other side. Right, and then on this side, I'm going to wind up with a negative 5y, a negative 6x, and a minus 1. Okay, so that's the isolate. And the last step is divide out dy dx. You get 5x minus 1. Okay, again, when you have dy dx by itself, right, this is minus 1 times dy dx. You divide out the dy dx, you're left with the 1. Okay, minus 5y minus 6x minus 1. I'm going to divide by 5x minus 1. Okay, so here's my expression for dy dx. And now I have to plug in the point 1 minus 1. So that's negative 5 times negative 1 minus 6 times 1 minus 1. 5 times 1. Okay, do stuff like this on your calculator. Okay, please just remember your numerator, if you're using a standard scientific, not a TI, you've got to parenthesize the whole numerator, parenthesize the whole denominator. A TI-84 has the ability to bring up a fraction template. Okay, for those of you with a TI, let me show you that. I have to share my TI with you. Okay, so I'm going to turn this on. Again, on a TI, you get to the fraction template using your alpha key. It's alpha, y equals, brings up this fraction menu. Just choose the first one, numerator divided by denominator. And then I can type this in exactly the way I wrote it. Again, remember on a TI, anything that's just in front of a number like this isn't a minus sign, it's a leading negative, this thing down here. Anything between numbers like this one is a minus sign. So leading negative, minus, minus. Okay, if you use the wrong one, you get a syntax error. Okay, what determines it is how many numbers are involved. If it's just in front of one number, it's a leading minus. If it's between, it's this symbol, the actual operation. So let me type this in, 5, parentheses, negative 1, okay, minus sign, 6, parentheses 1, minus 1. Okay, so it looks exactly like what I wrote. Then I have 5, parentheses 1. That's minus 1. All right. The other good news about this, it'll give you your answer as a fraction. You don't have to do math frac. Okay. So this says my slope is negative 1/2. Okay. If you're stuck using the Web 2.0 calculator, parenthesize the numerator, parenthesize the denominator, and then look up at the top of the screen and see that it rendered your expression the way you expect. Okay. I'm going to briefly show you that because I know not everyone has a TI. So I'm going to go back to my browser. Okay, here's the Web 2.0 calculator. You should have a link to that in your course. All right, and here's the way I would do this. I'd have to open a set of parentheses. Okay, and then with this one, I believe you don't put this in front. I think, oh, you can. Good. 5. That's leading negative sign 5, so that works the same way. Leading negative sign 1. So negative 5 times negative 1. Then I have a minus sign, 6 times 1. Okay, minus a 1. Close the numerator. Okay, divide by, now here comes the denominator, open parentheses. Okay, 5 times 1 minus 1. Close the parentheses on the denominator. Do you see how it rendered it like a fraction? This is what you need to check on this calculator to make sure it looks like what you expect. Okay, this should look like what you wrote on your paper. Okay, and again, this will probably render it as a decimal, but it does render it as a fraction up here. Okay, so this is almost as good as the TI-84, except you need to remember that a fraction bar is a grouping symbol. So if you don't have the ability to put a fraction template in your calculator, you need to use grouping symbols around the numerator and the denominator, so that the last thing the calculator does is the divide for the fraction. Okay? Everybody good with how we did this on a calculator? I want to make sure nobody gets balled up with arithmetic. Okay? Got my slope? Now, how do I have to find the equation of a tangent line. So I'm going to start with y equals mx plus b, because that's the equation of a straight line. I have m, I just found that out, it's -1/2, and I also have an x and a y. So I'm going to plug those in and solve for b. Okay, so my y value is -1, oops, sorry, -1. My m value is -1/2, my x value is 1. Okay, so this is -1 equals -1/2, which is -1/2 times 1 is just -1/2. And then you've got to add 1/2 to both sides, right? So -1 plus 1/2 brings the number closer to 0, right? It actually is -1/2. Okay, so again, your calculator, for the most part, can handle fraction arithmetic. Okay, I added 1/2 to both sides. Okay, it went away over here and made this -1/2. So here's my final equation. Y equals -1/2 x minus 1. Okay, and that is the equation of the tangent line to this curve. Okay. I find on these problems, most students get balled up with the algebra part, like, I'm not sure what to do once I get the slope. Okay, if you're more comfortable with point slope form, okay, use point slope form. Okay, I happen to just solve for b. It's easy, it's quick, and I'm good with it. Okay, but there are definitely other ways to get the equation besides the way I did it. Okay. Let's take a look at 3. Again, if you ever have questions, feel free to just shout them out, put them in the chat. Okay, but I'm not going to ask at every step, are you good with that? Is that fine? Okay. Find 2 positive integers such that the sum of the first number and 4 times the second number is 1,000, and the product of the numbers is as large as possible. Okay, so large as possible. Another word for that is maximize. Okay, maximize is something we know how to do with calculus, right? The product is something that I want to maximize, but I have a constraint. Okay, the constraint is this business up here. Okay, so I'm going to say let x be the first number and let y be the second number. Okay, and then my constraint says I'm going to add the first number and 4 times the second number. And that has to equal 1,000. That's a constraint. Okay, now remember how you do these application problems with calculus. You only know how to differentiate with respect to one variable, right? It's going to either be x or it's going to be t, okay? This problem has x's and y's in it. So what you need to do is to rewrite this, to solve for y in terms of x. Okay, and the reason you're doing that is you want an expression for the product. We know the product is xy, right? But I don't know how to differentiate that yet. Okay, and y is not necessarily a function of x here. Y is something totally separate. It's a separate variable. Okay, so what I need to do is write y in terms of x, so I only wind up with the variable x in my product. Okay, so let me do that. I'm going to solve this equation for y. Okay, so that is basically says subtract the x from both sides, and then divide both sides by 4. Okay, so again, if you rewrite this, you're going to get y equals, I'm going to divide each thing by 4. Okay, 1,000 divided by 4 is 250. And this is going to be 1/4 x. Okay, could you have also solved for y in terms of, could solve for x in terms of y? Yeah, sure. Actually, that would have been easier, right? Because this is by itself. The trick is get one variable. Okay, I don't care which variable you get. I just know most people are going to probably try to solve for y in terms of x. Right? Then my product, maximize xy, okay, but that's x times 250 minus 1/4 x. Okay, everybody all right with that? Everybody good with that? Okay. Then let's multiply this out. 250x minus 1/4 x squared. Okay, and now I need to differentiate this with respect to x. Okay, and then set to 0. All right, everybody all right with that? Okay, why am I differentiating it? I need to find its maximum. Okay, how do you find a maximum? You take its derivative, you set it to 0. Again, this is a quadratic. It doesn't have any undefined points in its derivative, so I don't need to worry about where the derivative's undefined. Just set the derivative to 0. So here's what I've got. 2/4 is 1/2 x. Okay, everybody good with that so far? Now what I'm going to do is I'm going to add the 1/2 x to both sides. So I get 250 equals 1/2 x. Now in order to solve for x, I need to multiply both sides by 2, right? 1/2 times 2 is 1. So I'll have 1x on the right. And 250 times 2 gives me 500. There's one of my numbers. Okay. It would also be a good idea if you checked your second derivative. Okay, so here's your first derivative over here, 250 minus 1/2 x. If you were to differentiate this again, the left-hand side, okay, what's the second derivative? What's the second derivative of that? If you differentiate it one more time, what do you get? Only one x term in there. What do you get? This is important, guys. Can anybody do the calculus on this, what I typed in the chat? If I differentiate 250, what do you get? 0. If you differentiate negative 1/2 x, what do you get? Yeah, it's negative 1/2, right? Because it's got a leading negative sign. Yes. Okay. And that's negative everywhere. Okay. Remember this? Second derivative negative, concave down. Okay. That means the function is concave down everywhere. Okay. And that also means your critical number gives rise to a maximum, right? The critical point is sitting at the top of the frown. Okay, so critical number is max. Okay, you should check, because it's possible if you have a complicated or a higher degree polynomial, you will get multiple critical numbers. The first derivative doesn't tell you it's a maximum. It tells you it's either a maximum, a minimum, or an inflection point, and you need to figure out which one. Okay? Now I realize in a lot of these problems, if you get one and the problem's asking for a maximum, most people say, hey, it's a maximum, I'm done. Okay, but again, remember, in the real world, it's not that simple. Okay, and the second derivative tells you about concavity, okay, and whether your function is a max or a min. Okay, so I just checked. Yes, this is giving me a maximum product. Okay, all right. That was only one of the numbers. How do I find the other one? Well, I use the equation that I created to solve for y. Okay, and I have y equals 250 minus 1/4 x, which is 500. Okay, this is 250 minus 125. Okay, which gives you 125. Okay, so your two numbers that you were looking for, 500 and 120. Okay, they satisfy the constraint that the first number, 500, okay, and 4 times the second, okay, which is another 500, will equal 1,000. You know that's true. And we figured out from the calculus that they give me a maximum product. They didn't ask me for the maximum product, but if they did, I'd just multiply 500 and 125. Okay? Let's take a look at number 4. Okay? Number 4 is one of those problems there's probably multiple ways to do, but I think the way I'm going to show you might be one of the simpler ways. Okay? And this is definitely a business type of problem, right? A hockey team plays in an arena with a seating capacity of 15,000. Okay? Why do they tell you that? Well, that's the maximum value of clients or customers you can have. When the ticket price is set at $12, geez, I'd love to know where this is, the average attendance at a game has been 11,000 people. Okay, so that's kind of, you can't fill the stadium, but you get reasonably good attendance. A market survey tells you that for each dollar you lower the ticket price, you'll increase your average attendance by 1,000 people. How should the owners of the team set the ticket price to maximize revenue from ticket sales? This is a real problem, okay? In other words, I want my revenue to be as high as it can be, okay? But at the same time, I want to get as many people in there. So what's the sweet spot? How much do I need to lower the ticket price that I get a maximum revenue? Well, let's talk about revenue. Revenue is price times number sold. All right? In this case, we're talking about tickets. Now, rather than letting my variable be like my ticket price, I'm going to say let X be the amount I need to drop the ticket price. Okay, so this isn't going to tell me the ticket price should be $10.50. It's going to say you should take $1.50 off the price of $12. Okay, so then let's come up with an expression for revenue, because that's the thing I'm going to have to differentiate to find a maximum, right? My price is going to be my average price, which is $12, minus however much I need to lower it by. Okay. The number I sell is going to be my average attendance. But remember, for each dollar, let's say X is in dollars, for each dollar I lower the ticket price, I'm going to get 1,000 more people above my 11,000 in the stadium. So the number sold will be 11,000 plus 1,000 X. Okay? Does everybody understand the revenue expression? Understand the revenue expression? I'll call it RX. Okay? It's price times number sold, but again, X is how much I'm taking off the ticket price. Anybody questions on this? Okay. All right, let's do some algebra. Okay, this is a product of binomials, which of course you could FOIL out. Okay, I'm going to multiply 12 times 1,100. That's going to give me 132,000. Okay, this will give me minus 11,000, and this will give me plus 12,000, right? See my inside terms? Okay, one's plus 12,000, one's minus 11,000. That nets out to 1,000x. My last term, one's negative, one's positive. I have a negative x and then a positive 1,000x. Okay, that's going to be negative 1,000x squared. Okay, because again, I'm multiplying. All right, so that's my revenue polynomial. It's quadratic. Okay, let's differentiate it. Okay, because I need to find its derivative. Differentiate because I want to find the maximum. Okay, so R prime of X, that first term is a constant, so I get nothing out of it. The second term just gives me its coefficient. And the last term is where I get the interesting stuff. Bring down the 2, multiply the 1,000, and drop the exponent by 1. Okay, set R prime of X to 0. Again, everything's a polynomial. Don't need to worry about undefined derivatives. Okay, I'm going to bring the 2,000 over to this side. It becomes positive. Right, and then I'm dividing everything by 2,000. So X equals 0.50. Okay, I didn't say 1/2 because X is a number that means money. Okay, so what this is saying is I need to drop my ticket price by 50 cents. Again, did that really give me a maximum? Check the second derivative here. Okay, if I differentiate this left-hand side, I get 0 for the 1,000 and negative 2,000 for the second term. Again, second derivative is negative. It gives me a maximum. Okay, it's always a good idea to check that. If your second derivative is negative, you're getting a maximum. Okay, so that means I should drop my ticket price. Ticket price is going to be $12 minus 50 cents, $11.50. They asked for that. Okay. And they didn't ask me for the revenue, but if you did want to figure out revenue, okay, you would basically have to take your maximum revenue, okay, which is $11.50 times how many people could you pack in? Well, remember, we said anything you increase your revenue, your ticket, drop your ticket price 50 cents, okay, that means you get half of another 1,000 people. So this is going to be, that's this expression over here on the right side, okay? So 11,000 plus 1,000 times half, 0.5, that's going to give me 11,500 people for a total revenue of $132,350. Okay, they didn't ask for revenue, okay, but you could find it. This is what they asked for. Okay, anybody questions on number 4? Okay, it is my goal to try to get to at least number 8. Okay, so we have another 4 problems to do. Okay, I'm going to try through number 8, and all solutions will be uploaded. Okay, so I'm trying to get through number 8 by 10:30. Okay, all right, so feel free, shout out any questions. Okay, again, a lot of these are applied problems because that's kind of what you use this for. Nobody's going to come and ask you to, find the derivative of this. Nobody asks you that. They ask you, can you help me figure out what the maximum profit's going to be if we drop our cost by so much? That's what you're going to need to do. Okay, so here we have an aquarium. Okay, we're assuming it's a rectangle. It holds 40 cubic meters of water. Okay, so again, assume rectangular. Oops, hold on. Rectangle. Okay, so we're assuming a rectangular base, and let's assume it looks like this. Hold on. Oops. All right, so let's say we have a rectangular aquarium, and the length of its base is twice its width. Okay, so let's say here's the width, and I'm going to just call that 2W. Okay. If the material for the base costs $20 per square meter, the base has to be stronger, let's say, okay, because there's more downward pressure there, okay, and the material for the sides costs $16 a square meter. Please notice these units are area units, okay. Find the cost of the materials for the cheapest such aquarium. Okay, now, cubic meters is a volume measurement, right? Okay, we're missing one of the dimensions of the aquarium. Which dimension are we missing? Which dimension of the aquarium are we missing, folks? Remember, it's a 3-dimensional thing. We've got its length and its width. We need its height, right? Okay, where are we going to get that from? We're going to get it from the volume. Okay, a volume of an aquarium is length times width times height, right? It's a rectangular box shape. So you basically find the area of its base, multiply by its height. Okay, we also know 40 equals, okay, now my length I said was 2W times width times height. Okay, where did I get the 2W from? They said the length was twice the width. All right, so this becomes 40 equals 2W squared H. And now it's real easy to solve for H. 40 over 2W squared. Okay, equals H. Divide out a 2. 20 over W squared equals 8. Again, you've got to use what they give you to figure out what's missing. Okay? So now I know my height. I'm going to erase this over here. And I'm going to put it's 20 over W squared. That's my height. Okay? Now, I need some feedback from you. What are we trying to find? What are we trying to find? Are we trying to find a volume? Are we trying to find an area? Are we trying to find a cost? What are we trying to find? Anybody? Guys, there's like 13 of you on. You're trying to find price, cost. Yes. Lowest cost. Thanks, Benjamin. Lowest cost. Okay. So that means minimize cost. Okay. Minimize. Okay. Well, is the cost dependent on the volume of this aquarium? What are the costs given in? They're dollars per what? Square meter. Okay, so cost depends on surface area. Okay, remember the sides of this thing are cheaper to build than the base that's sitting on the floor or the table or whatever. Okay, so let's figure out expressions for area. Area of the base, that's length times width. Okay, and that's easy because we already know that it's 2W times W, so 2W squared. Okay, cost of the base is going to be $20 times whatever that area is. Okay, everybody all right with that? Now, if you think about a rectangle, the opposite, a rectangular box, the opposite sides are the same shape. Okay, so if you look at this side over here, this side is 20 over W squared by W, whereas this side is 2W by 20 over W squared. Okay, so you have to be able to kind of switch the figure around in your mind. Okay, so again, let me put a line under here, area of sides. Okay, there's two sides, 2 times 20 over W squared times W. Okay, that's this side here and that side in the back, front and the back. Okay, there's two of those. Okay, and I'm just multiplying the length times the width. And there's also two of the sides that are facing out of the page, right? And they're 20 over W squared times 2W. Okay, let me do a little algebra because I'm positive this can be simpler. Okay, 2 times 20 is 40. And notice, one of these W's is going to cancel out, right? So this is going to be 40 over W. And this is going to be 2 times 20 is 40 times another 2 is 80. And one W will cancel out. Okay, and I'm just using algebra. I haven't done any calculus yet. This is all algebra. Okay. These things both have the same denominator, so I can add the numerators. Okay, and 120W is an expression for the sides of the aquarium. Okay, cost of the sides. And we said all of the sides cost me $16, so 16 times 120 over W. Okay. Okay, that's 1920 W. Okay, so I have my two costs. One's 40W, one's 1920 over W. So now the cost of the whole thing as a function of W is, that again, 40W squared plus 1920 over W. Okay, so now I have my expression for cost. Is everybody okay with the cost? Again, there are a couple of things you had to realize to do this problem. You had to realize they gave you the volume so you could find an expression for height in terms of W. Other than that, you're not doing anything with the volume. The second thing you had to realize was cost is dependent on surface area. You need to be able to figure out the surface area of a box. Okay. And then the last thing you had to realize was the different costs need to multiply your area so you can get a cost expression. Okay. All right, so here's the thing I need to actually differentiate. All right, and again, rather than write 1920 over W, I would probably rewrite this like this. I haven't done calculus yet. 1920 W minus 1. Again, I'm doing that to make calculus easy. Now, finally, I'm doing calculus. This is going to give me 80W, and this is going to give me negative 1920 W minus 2. Okay, everybody good with that? Again, the only thing I have to be careful is my cost function is undefined when W is 0, but that's good because W has to be bigger than 0 or I have no box. Okay, so I don't have to worry about undefined derivatives. I'm not going to take the solution W is 0. Okay, so let's set to 0. 80W. I'm going to rewrite this as 1920 over W squared. Okay, I'm going to add the 1920 over W squared to both sides. Okay, and now I want to solve for W. Okay, so algebraically, what's the next step? Okay, what's the next step algebraically? Here's where I am right now. Anybody want to shout out, what should I do next? Divide by 80? I'd rather get rid of my denominator first. How would I get rid of w squared in the denominator? Well, it's dividing 1920. So how do you get rid of the divide, folks? Yes. Okay, so w squared times 1920 w squared equals 80w times w squared. Okay, and like magic, we get rid of that. 1920 equals 80w cubed. Okay, now I'm going to take your advice, Benjamin, and I'm going to divide by 80. Okay, and if I were you, I wouldn't simplify this necessarily. Okay, I would say take the cube root of this whole fraction. Let me bring up my TI to show you what I mean. Okay, so cube root is on your math menu. See it right here, number 4. Oops, clear. Sorry. Cube root of, and then you can put parentheses, or you can even use your alpha y equals 1920. Okay, so I'm getting about 1.33. Okay. Oh, I said it wrong. Sorry. Second entry. Fat fingered it. I lost my 0. I was going to say that's awfully small. Hold on. There's my 0. There you go, 2.88. Okay, so cube root of both sides. Okay. Now, what they asked you for in this problem was the cost of materials. Okay, see it says cost of materials. So we're not done yet. I have a W value, but now I need to actually figure out the cost of all the materials. Okay, so the cost for the base, I'm going to plug in my W here, 40 times 2.88 squared. Okay, and that's 331.78. Again, I did this on a calculator earlier. Here's the cost for my sides, 1920 divided by 288. And again, these are approximate, rounded to the nearest cent. Okay, so my total cost for the aquarium is 331.78 plus 667.67. So this thing is actually going to cost almost $1,000 to build. Okay. Now again, remember your widths are in meters. Okay, they didn't ask you for the actual lengths of the widths or anything. They asked you for cost. Cost of materials, okay? So again, this is in dollars. Okay, so this is a big aquarium, like this is almost 3 meters long. A meter is about 3 feet. So this is like a 10-foot, 10-foot by 20-foot aquarium, the kind you might find in a museum, okay, or an actual aquarium itself. Okay, it's a big aquarium, so that's why it's so expensive. Okay. Questions on the process. Now, again, what I'll do when I go through this is I'll put numbers on it, like here, first, second, okay, and then here's 3, okay, 4, the steps, okay, and then total cost. Here's 5, 6, and last but not least. So there's a lot of steps in this problem. Okay, my advice to you when you're doing the exam, okay, spend the majority of time on the applied problems. Make sure you're comfortable enough with the basic stuff, like the implicit differentiation and taking an integral, that you don't have to waste a lot of time on those problems. Okay, you don't want to waste a lot of time on those. You want to spend the majority of your time doing this. Okay. Anybody questions on the aquarium? Questions at all? No. All right. Here we have something that's actually changing shape. We have the volume of a cube is increasing at the rate of 10 cubic centimeters a minute. Okay, so let me try to draw something roughly like a cube. All right. How fast is the surface area increasing when the length of an edge is 30 meters? Okay. They're giving you a rate for the change in volume. This is dV dt, because they're looking at what the units are in. Volume's in cubic centimeters, time is in minutes. And they give it to you with rate units on it. So you know right away it's a rate. Okay? Now they're saying surface area, how fast is that increasing? So they're asking you for a rate. Okay? Let's call that dA dt. Okay? So they want to know how fast is the area changing. Okay? So what's happening here is this cube is, think of it as if it was inflated and it's growing. Now every side of this cube is the same. Okay? So we only have one variable. And we know S is 30 centimeters at the instant we're asking the question. Okay? What's the surface area of a cube? Well, think of it. It's like a 6-sided die, right? And each area, each face of the die has an area of S times S, or S squared. So the surface area is 6S squared. Both of these are functions of time. So if I differentiate this side, I'm going to get dA dt, which is what I want. Yay. But if I differentiate this side is going to give me ds dt, which I don't have. Again, why am I going to get ds dt? Because S is a function of time. And when I differentiate implicitly, I'm going to get ds dt from the chain rule. Okay? So my question to you right now is, where am I going to get ds dt? In other words, the rate of change of one of the sides, the length of one of the sides. Where am I going to get it from? Can anybody come up with anything? Well, you're interested in surface area. What other information did they give you? They gave you information about volume, right? But they gave you the rate of change of the volume. Okay, so think about it like this. Volume of a cube is its length, its width, and its height all multiplied together. So there's an equation that tells you the volume of the cube. What happens if we differentiate this implicitly with respect to time? Well, this is going to give me 1 dV dt. If I differentiate the x cubed, well, the derivative of the outer function is 3s squared, and the derivative of the inner function is ds dt. Now what I can do is I can substitute the values I know from the problem, namely that dV dt is 10 and s is 30. And I can solve for ds dt. Okay, so let me plug in what I know. This is 1 times 10, 3 times 30 squared, ds dt. Okay, so I've got 10 and 3 times 30 squared is 27,000 ds dt. So ds dt is 10 over 27,000. Okay, I'm going to approximate it by a decimal. Okay, which gives me 0.0003. That ought to be enough places for accuracy. Okay. You can, yes, you can say it's 1 over 2,700. You can carry it as a fraction if you want. Keep it exact. But I'm keeping it like this. Okay. Now I can finally do what they wanted me to, which was to differentiate my area. Okay. Again, because I'm trying to find dA dt, which is 1 times, right? dA dt is the derivative of area. And now if I differentiate the other side, I have 2 times 6 is 12, s ds dt. Okay, so plug in s ds dt. Okay, so dA dt equals 12 times 30 times 0.00037. Okay, and if I multiply that all out, sorry, I get, let me make sure I get this right. Times 30. Okay, so I get a rate of 1/10 of a centimeter squared. Anybody questions on this one? Okay. Sure, we're good with this one? I realized I screwed up a power of 10 here. Okay, 3 times 30 squared is 2,700, not 27,000. So I'm just going to drop everything, get rid of the zero everywhere. Watch how this changes things. This is sometimes useful to see how things screw up. Okay, so I'm making my rate larger, which means my rate in my area is going to be larger too. So this 1 comes on the other side of the decimal point. Okay, so again, I apologize for that. Okay, but again, this is not 27,000, it's 2,700. All right, so again, suppose you made the same mistake on the exam. You would get like 9.5 out of 10 points because it's a silly arithmetic mistake. And again, that's why I ask you, show me your work. Okay. My objective here is, do you know how to solve the problem? Again, arithmetic is something we can offload onto a calculator. Okay. All right. Here's the last one I think we're going to have time to do. Okay. The one, number 8, I'll show you how to set it up, and then I'll upload the work so you can see how it's done. But this is the last applied problem, and I think it's important to understand how to do it. The demand function for certain product is given by, and they're missing in here for some strange reason in this copy, we're missing P of X. It should be P of X. Okay, and that will show up. Okay, so this is kind of relating price to the quantity that we're selling. Okay, and this is the quantity demanded. The costs associated with the product are given by this equation. So here's our fixed cost, our variable cost. Okay, and X is the quantity demanded. If production of this product is increasing at a rate of 50 units per week, so 50 units per week is our rate, okay? You have to kind of figure out what we've got here, okay? So this is what? This is D X E T. Find the rate of change of profits when X is 1,000. Okay, so again, look for the word rates. Okay, these are both changing with respect to time, so I'm thinking maybe implicit differentiation. But the first thing I need is a profit equation. That's revenue minus cost. Well, they gave me a cost equation, so I'm good there. I don't have a revenue equation, so I have to build one. Okay, remember from our example with the hockey arena, revenue is your price times how many you're selling. Okay, so this is going to be price times X. Okay, they gave me a price equation, so I'm just going to multiply that by X. Okay, so my revenue equation is that. All right, so I have two equations that I need for profit. My P of X equals R of X, C of X. Right, here's the R of X. Okay, so I have 0.24x minus 2x. Put the minus sign for profit, but then remember the whole cost equation needs to go in parentheses. Okay? Everybody all right with that? Right, so my profit equation, if I look at this, okay, this is a square. Okay, so there's no other squared term in my cost equation. So this 0.24x squared is going to wind up in my profit equation. Then I have negative 2x minus 0.12x. Okay, but it's minus, minus again. So they're both negative. Okay, so I'm taking another 0.12 from negative 2. So minus 2.12x. Okay, and then the 890 will also have a minus sign in front of it. Again, so remember, distribute your negative signs. Okay, just trying to make sure I have the right profit equation. Okay, then I want d2 dt. Okay, so I want the derivative of profit with respect to time. So I'm differentiating my x's with respect to time. All right, so first I differentiate the outside. That's the outside function. Here's the inside function. Okay, and if I differentiate the outside function, and then the inside function. Okay, the 890 doesn't give me anything. All right, the rest is plug in your dx dt value, which they gave me as 50. Okay, everybody understand where the dx dt is coming from? So again, I have, 0.48 times 50 minus 2. Okay, so I'm getting negative 82. Okay, but again, they want to know I'm missing some stuff, right? Because again, there's an x in here. All right, so let me put the x over here. Okay, so this is x. And then I have the 50 out over here. Okay, so they want to know when x is 1,000, what's happening to my profit. Okay, so it's not just dx dt here. Don't forget you've got an x in your answer. Okay, so when I do that, that makes things look a lot rosier. Okay, so I'm getting a positive increase, right, with respect to time. Okay, and this is in weeks. Okay, so this says when I make 1,000 of these things, okay, I'm going to have an increase in profit of $23,894 per week. Okay, so the process was identify your rates. Okay, you want to find the rate of change of profit with respect to time. You're given the rate of change of production, which is X. Okay, build your profit equation. In order to do that, you needed to build revenue from price. Okay, so cost, price is revenue minus cost is profit. Then differentiate it implicitly. Don't forget your dx dt's and don't lose your x like I almost did. Okay. Anybody questions on number 7? Questions on 7? Okay. Last one I want to show you is this one. These are Riemann sum problems where they want you to evaluate a Riemann sum. Remember what these are. These are approximations of a definite integral. So what I suggest you do with these problems is actually graph, okay, I gave you a Riemann sum calculator, so technically you could even use that. Okay, it's in the course. Okay, but if you want to try it yourself, okay, actually graph this with a graphing calculator. If you were to graph this function, it would look something like this. So I have 1 and 2. That's the range I want to, the interval I'm graphing on. So this function would look something like this if I graphed it. Okay? And then they want you to use 4 right endpoint rectangles. Well, in order to get 4 of them in here, I'm going to have to divide these in half, right? So this is going to be 0.5. This is going to be 1.5. Now, right endpoint rectangles means the right endpoint of each rectangle needs to sit on the curve. So here's the first rectangle. Okay, the second rectangle has no height. Okay, the third rectangle is going to look like this. And the fourth rectangle is going to look like this. Okay, and then to evaluate the sum, just do something like this. Here are your x values, your f of x values, and then the area. Okay, I'll just show you the first one. Okay, my x value here for the left endpoint rectangles, right endpoint rectangles is 0.5. Okay, then 1, then 1.5, and 2. Okay, then you just evaluate the function at each of the x values. If I plug in 0.5 here, okay, I'm going to get negative 0.25. Okay, if I plug in 1, I get a 0. If I plug in 1.5, I get 0.75. And if I plug in 2, I get 2. Okay, where am I getting the f of x's from the function? Okay, area is just x times f of x. All right, so you're just going to multiply these. Okay, so negative 0.125, 0.375, and this would be, oh wait, okay, it's not the x value, it's the size of x, it's dx. So each one of these is 0.5. Okay, so 0.5 times negative 0.25, 0.5 times 0, 0.5 times 0.75, and half of 2, which is 0.5. Okay, so again, you have to think that each one of these dx equals 0.5. Okay, they're not one y, they're a half y. All right, and then your value of the Riemann sum would be the total. Which I got to be 1.2. Right. Questions about Riemann sums? Anybody? And again, there's an app I gave you a link to that will do this for you. Just make sure you pick the right endpoint. Okay. The app gives you a choice between left, right, and middle. Okay. Okay. No questions on the Riemann sum? Okay. Again, remember areas that are below the x-axis have negative signs. Okay. All righty. I am going to come back to our meeting. Stop sharing. Okay, and ask if there are questions about anything. Okay, again, I skipped all of the integral stuff because I'm pretty sure everybody can do that.